Assalamualaikum. Our group will present about differential equations using eigenvalue problems in structural engineering. Introductions. Solving differential equations using eigenvalue problems in structural engineering is a powerful mathematical approach that helps engineers analyze the dynamic behavior of structures under various conditions. So this approach allows engineers to analyze the dynamic characteristic of complex structures in a systematic manner and providing insight into potential resonance. And this method is particularly crucial for designing structures that can withstand dynamic loads such as earthquake, wind, or other external force.
Next, let's we move to the methodology. So firstly, let's consider a simple example of a vibrating system modeled by a second order linear differential equation. Suppose we have a single degree of freedom system, such as a mass spring damper system, by the following equation. So here is the equation: md square over dt square plus cdx over dt plus kx equal to 0, where m is the mass of the system, c is the damping coefficient, k is the spring constant, x is the displacement of the mass from its equilibrium position, and finally t is the time. We can rewrite this equation in matrix form by introducing the vector u equal to s and s dot transpose, where s dot is the velocity. The equation will become m du over dt plus cu plus ku equal to 0. Here, m, c, and k are matrices defined as follows. M is equal to m001, c is equal to c000, and finally k is equal to k000. After we transpose the matrix U, it will become like this. So we let ut equal to ht and s dot t, and we differentiate u with respect to time to obtain the acceleration u double prime. The differential equation can be written as mu double prime plus cu prime plus ku equal to 0. This is the matrix form if of the original differential equation, and the subsequent steps involve assuming a solution ut equals to v exponential to the power to st and solving the resulting eigenvalue problem. So the eigenvalue problem is determinant s square m plus sc plus k equal to 0. The solution for S in the characteristic equation are the eigenvalues, and the corresponding eigenvectors V provide information about the mode shapes of the vibrating system.
Let's do a scenario example with values for the mass, damping coefficient, and spring constant. Moving to the example, suppose we have the following values: m equal to 1 kilogram, c equal to 0.1 Newton meter per second, and k equal to 10 Newton per second. So in structural engineering, the given matrices are crucial in representing the dynamic behavior of a system through the matrix equation. M du over dt plus cu plus ku equal to 0. Here is a breakdown of each matrix and its role. Mass matrix M equal to 1001 represents the distribution of masses in the system. In the context of differential equations, it's used to describe the inertial forces acting on the structure. So second one, stiffness matrix K. K equal to 10,000 describes the stiffness of the structure. The non-zero element 10 indicates a stiffness associated with the first degree of freedom. The second degree of freedom has zero stiffness, implying it's a free degree. The third one is damping metric C 0.1000 represents damping in the system. Here, damping is applied only to the first degree of freedom, and the second degree is undamped. The matrix equation combines the effect of mass, damping, and stiffness in the dynamic analysis of the structure. Solving this equation involves eigenvalue problems to find the natural frequency and mode shapes of the system. The eigenvalues represent the squared natural frequency, and the corresponding eigenvectors provide information about the mode shapes. So these matrices and the associated differential equation are fundamental in understanding the dynamic responses of structural systems, especially when solving eigenvalue problems to analyze the system's natural frequency and mode shapes. The next one, when assuming ut equal to xt, vt, e to the power of st, and substituting it into the matrix equation, m du over dt plus cu plus ku equal to 0, we get dt s square m plus sc plus k equal to 0. So, in this equation, this determine it is a characteristic equation that derive from the matrix equation. Solving this equation for S involves finding the eigenvalues of the system. The roots of this characteristic equation represent the natural frequencies of the structural system. By solving for S, we can obtain the complex frequencies associated with the system's dynamic response. In structural engineering, this process is integral for understanding the system's behavior under dynamic loading conditions and is often used to identify critical frequency that may lead to resonance, or other significant responses. So, as mentioned earlier, by solving eigenvalue problem, we need to solve for the S in the characteristic so that it will yield eigenvalue. Solving the S can eigenvalue for the value S1 and S2. So, as presented in the slide, the given complex conjugate eigenvalues S1 equal to negative 0.05 plus 3.1623i and S2 equal to negative 0.05 and negative 3.1623i. In this complex conjugate eigenvalue, it have the several implications in the context of structural engineering problems, where eigenvalues form characteristic equation. The characteristic equation is obtained by setting the determinant of the matrix S square m plus SC plus k equal to 0. Solving this equation results in the eigenvalues, which in this case are complex conjugate pairs. For the second one, the nature of eigenvalues. The real part, negative 0.05, represents the damping effect on the system, while the imaginary part, positive 3.1623i, denotes the oscillatory nature of the response. The third one is the natural frequency, where the imaginary part of the eigenvalues, positive 3.1623i, corresponds to the frequency of oscillation. In this context, the natural frequencies associated with the systems are approximately 3.1623 radian. The next one is the damping ratio, where the real part, negative 0.05, is related to the damping ratio of the system. A small negative real part indicates underdamping. The damping ratio can be calculated as the ratio of the real part to the magnitude of the imaginary part. In this case, 0.016, which suggests low damping. So the complex conjugate eigenvalues S1 and S2 provide a comprehensive understanding of the dynamic behavior of the structural system, including the natural frequencies, damping characteristics, and mode shapes. After all the conclusion, we can discuss that eigenvalue S1 and S2 represent the natural frequencies of the system. In this scenario, the system exhibits two modes of vibration with frequencies determined by the real and imaginary parts of the eigenvalue. Next, mode shapes. The corresponding eigenvectors will provide information about the mode shapes, illustrating how they must vibrate at these natural frequencies. So the next one is system behavior, where the imaginary part of the eigenvalues indicates oscillatory behavior, while the real part indicates damping. The system is underdamped, and the complex eigenvalues characterize the harmonic motion of the mass. And last one is practical implications. Understanding the natural frequencies and mode shapes is crucial for designing structures that can withstand dynamic loads without experiencing resonance. Engineers can adjust the system parameters to avoid resonance and ensure structural stability.
Okay, in conclusion, using engineering problems to solve a differential equation is a powerful and efficient method in structural engineering, essential for designing structures to withstand the development earthquakes. This method highlights the efficiency of mathematical models in analyzing real-world phenomena, while also giving engineers a powerful tool for safe and durable design, but also promotes structural engineering. If by using resources as efficiently as possible, engineers can contribute to sustainable development by creating structures that are powerful, dependable, and cost-effective. So, Solving differential equations based on eigenvalue problems is not just a mathematical scheme, but an important means for making the world safer and stable.